The main goal of part 2 of my talk is now to discuss how CMC surfaces in hyperbolic space can be obtained as surfaces of rolling. So we will first discuss the rolling construction for curves and surfaces in general in Euclidean space, and we'll then discuss how these constructions are helpful to generate CMC surfaces in hyperbolic space. To start with, we will have a look at curves in the Euclidean plane. So our ingredients are two curves, one curve gamma, which is fixed during the whole rolling process, and one curve that is rolled, which we will denote by gamma hat. So we have given a curve gamma, given by a parametrization from an open interval I into R2. And without loss of generality, we assume that gamma is parameterized by arc length. And then any curve gamma hat, which is also parameterized by arc length, can at least locally be rolled onto gamma. And by rolling, I mean that pointwise gamma hat and gamma are aligned, as well as we align the tangent direction and one distinguished normal direction. So the motion of gamma hat can be described by a one-parameter family of Euclidean transformations in the plane. And this is given by the following data. Motion of gamma hat at any point t0. We require the following. We require that the point gamma hat at t0 is mapped onto gamma t0. Then the tangent directions are aligned. As well as the normal direction. And this one family of Euclidean transformations now describes uniquely the rolling of the curve gamma hat onto gamma. With this rolling, we generate further curves, namely a two family of so-called curves of rollings. Often they are also called roulettes. And those curves are described by the choice of one initial point. And then the curve of rolling is given by the trace of P0 under this one family of Euclidean transformations. So the trace P0 under Euclidean transformations provides a further curve. And of course, in this way we obtain a two family of curves of rolling in the Euclidean plane. So let's recall what were the ingredients for the curves case here. So we started with a fixed curve gamma, and required that the curve gamma is parameterized by arc length, then we had one curve gamma hat which was rolled onto gamma with the same arc length. And then we obtained a one family of Euclidean transformations, and for any initial point P0, we obtained as a trace further curves in the plane. If we now want to roll two surfaces onto each other, the ingredients are quite similar. We fix one surface sigma in Euclidean space. However, if we want now a well-defined rolling of the second surface sigma hat onto sigma, we have to require that sigma hat is isometric to sigma, in the sense that the first fundamental forms of sigma and sigma hat coincide. If this is the case, then we get a well-defined rolling, and this is again defined by Euclidean transformations. In this case, we get a two family of Euclidean transformations. And at any point T0 in M, the Euclidean transformation is described by the following data. The surface points are mapped onto each other. We align the two tangent directions. And the normal direction of the two surfaces. And again, from this two-parameter family of Euclidean transformations, we can induce a three-parameter family of surfaces of rolling. And these are determined by the choice of an initial point. Then the trace of P0 under these Euclidean transformation then give a unique new surface. In our setup, the next question is then of course about the reverse construction. So given a surface F, in our case then a CMC surface in hyperbolic space, is there a pair of surfaces that generate F as a surface of rolling? So can we find a pair of surfaces that are isometric, such that for the right initial point, the rolling construction then exactly yield the surface F? The answer to this general question was given a long time ago by Bianchi and by the following theorem. Given a surface F, which is without loss of generality parameterized by curvature line coordinates, and if we denote the first fundamental form of F by E du plus G dV, then any scalar solution T of the following equation here gives rise to a pair of isometric surfaces that generates F as a surface of rolling. In this equation here, kappa 1 and kappa 2 are the two principal curvatures of F. Curvatures of F. And the two surfaces sigma and sigma hat are then given by the following constructions. Instead of t, it's a bit more comfortable to look at the function r, which is given by 1 over t. Then the first surface sigma is given by f plus r n, where n is the unit normal field of f. So we have our surface f with the unit normal field n. And then the surface sigma is given at the distance r here. So this is my first surface sigma. And then we have to construct the second surface, sigma hat. This is a bit more complicated. And this starts with the following observation. The first fundamental form of the metric I hat, defined as 1 over R2, times the metric of sigma minus dr squared. This metric here has constant Gaussian curvature 1 in Euclidean space. This follows from the equation from above. This can be computed explicitly. So this metric here, I hat, has constant Gaussian curvature 1. And this means there exists a parametrization small m from M2 into the 2 sphere. So on the 2 sphere, this metric here uniquely determines a parametrization, which we denote by n. And then sigma hat is defined as r times n. After the theory about rolling of general surfaces, I now want to specify the CMC surfaces in hyperbolic space, and would like to give an explicit construction that yields those CMC surfaces as surfaces of rolling. And this construction will rely on the Darboux transformation discussed in the first part of this talk. So what was the story? The story is you can start with a conformal map in the plane, then make a Darboux transformation of that conformal map. One obtains a second surface, and this second surface is then always a CMC surface in a hyperbolic space. And the main properties of the Darboux transformation is that both surfaces envelop a common sphere congruence, these two family of gray spheres here, such that curvature lines on the two envelopes correspond. And additionally, the two first fundamental forms on the two surfaces are conformally equivalent. And the idea for our rolling construction is now we look at the center surface of the common sphere congruence. So on the centers of these spheres, this gives of course a surface, which we call center surface. And the idea is, for our rolling construction, we find surfaces that are isometric to the center surface, such that rolling then yields the conformal Gauss map and the CMC surface. So let us start to have a closer look at the hyperbolic Gauss map. So we start with a conformal map in the plane. This is determined by a metric. Let's denote that by E2 phi du squared plus dv squared. And considered as surface in Euclidean 3 space, this conformal planar net has vanishing principal curvatures. And then Bianchi's formula tells us how to determine all pairs of isometric surfaces that generate this conformal planar net via rolling. And in our case, this formula simplifies because we know that E equals G equals 2 E2 phi. So this one here becomes 1. This factor here becomes 1. And moreover, we know that the two principal curvature vanishes. So this becomes 0, this and this as well. So this formula here simplifies to duu logarithm of t plus dvv logarithm of t equals minus exponential 2 phi times t squared. Then let us denote this part here by delta ln t. So if we start with a conformal map in the plane, any solution T that satisfies this equation here, which we denote by star, will give rise to one surface pair sigma and sigma hat that are isometric, and these two generate the conformal map via rolling. So probably this equation here looks familiar to you from a differential geometric point of view. Namely, there is the following well-known fact. If we consider a conformal metric, g squared du squared plus dv squared, conformal, then the Gaussian curvature of that metric which is already well defined by the first fundamental form of the surface. This Gaussian curvature satisfies the following condition: delta ln g equals minus Gaussian curvature k times g squared. In particular, for our planar net here, we learn that delta ln e phi vanishes. Right, and this fact gives us now a way, or a geometric way, of understanding solutions of that equation. Namely, we can write a function w, or we define a function w as e phi t. Then the equation star becomes delta ln e minus phi w equals me minus e 2 phi times e minus 2 phi w squared. Then these two cancel. Further, we know that this part here vanishes, so we are left with delta logarithm of w equals minus w squared. But now this equation here tells me that a metric IW of the form w squared du squared plus dv squared has constant Gaussian curvature 1. So in summary, we have learned that if we start with a conformal map in the plane, then any metric IW with constant Gaussian curvature 1 yields a solution T defined as W e minus phi of the equation star. So we have now seen that for any conformal map in the plane, there exists many pairs of surfaces that generate the conformal map as surface of rolling. Our question is now, which of these pairs of surfaces generate exactly the Dabou pair consisting of the hyperbolic Gauss map and its CMC surface in hyperbolic space? And the sought after pair of surfaces can be obtained by another transformation for isothermic surfaces, namely by a so-called T transformation. Any Dabou pair of isothermic surfaces f and f hat envelopes a common sphere congruence, which comes then with a radius function r. And using this radius function, one can build further isothermic surfaces. For example, there is one specific isothermic surface that belongs to F and is given by the following metric and the following two principal curvatures. Of course, this construction here is symmetric, so we can also make a collapsal transformation of the second surface, so of F hat, to obtain a new isothermic surface F hat trittles. So, starting with a Dabou pair consisting of a hyperbolic Gauss map and one of its CMC surfaces in hyperbolic space, one can make a T-transform of the conformal hyperbolic Gauss map to obtain a new isothermic surface given by the following data, which in this case even simplifies a bit because our hyperbolic Gauss map has vanishes principal curvatures. So kappa 1 and kappa 2 vanishes, so I'm getting here kappa 1 twiddles equals mu equals kappa 2 twiddles. So we're getting here a totally umbilic surface patch. And out of that surface patch, or from that surface patch, we can take the Gauss map, which is in this case just a scaling, that yields a map on the S2, and which we denote by small n. And then since on this surface patch here on the T-transform we have curvature line coordinates, we can simply compute the metric of the Gauss map, which is nothing else than the third fundamental form of my surface F twiddles. This is IN, and this is nothing else than mu squared over lambda squared times E2 phi over du squared plus dv squared in this case. So this is 1 over the radius squared times the metric of the hyperbolic Gauss map. And if we construct now with this Gauss map N our surface sigma hat, which then becomes one surface in the construction of rolling, then we define sigma hat as R times N, and we compute that the metric I hat of that surface equals dr squared plus r squared times the metric of the Gauss map, IN. Of course, this is then nothing else than dr squared plus the metric of the Gauss map IN is 1 over r squared I, so this gives plus the metric I of the hyperbolic Gauss map. On the other hand, if we look at the center surface, so on this surface here, that is given by the centers of the spheres that are enveloped by the Dabou pair, then this center surface here, which we denote by sigma, is given as F, the hyperbolic Gauss map, plus the radius times capital N, where N denotes the constant Gauss map of F. If we then compute the metric of this center surface, then we obtain as metric I sigma nothing else than I plus dr squared, and we immediately see that the metric of sigma and sigma hat coincide, so sigma and sigma hat are indeed isometric surfaces, and one can then prove that sigma and sigma hat constructed via the T-transform yield the hyperbolic Gauss map as surface of rolling. So now sigma and sigma hat generate the hyperbolic Gauss map F as surface of rolling for the right initial point. A similar construction can be now done for the CMC surface in hyperbolic space. Namely, if we denote the CMC surface maybe by G, then we can make a T-transform of G to obtain a new isothermic surface G twiddles, and we take again from this surface G twiddles the Gauss map, which then yields a second map in the S2 and from this Gauss map and twiddles, we then construct surface sigma twiddles via R and twiddles, and then one can prove that the center surface sigma together with sigma twiddles generates the CMC surface via rolling. So this construction now gives a way of generating any CMC surface in hyperbolic space as a surface of rolling. For the experts, I want to point out that there are classical permutability theorems, and there is one available between T transforms and the Dabou transform, and the permutability theorem in this case tells us that these two surfaces here are related by a Christoffel transformation, showing in particular that since we have here a spherical patch, we obtain here that as G twiddles a minimal surface, which is then the minimal cosine of the CMC surface in hyperbolic space. Further, I want to point out that there is a different construction for CMC surfaces as rolling surfaces given by the Bianchi-Callot formula, which also shows that CMC surfaces in hyperbolic space can be obtained via rolling, but with the Bianchi-Callot formula, in general, you don't get curvature lines on your CMC surface, but some different coordinate system. So in general, this gives you the same CMC surfaces in hyperbolic space, but for different parametrization and not related to a Dabou pair as we have it here. So this was my talk about CMC surfaces in hyperbolic space as surfaces of rolling, and I would like to thank you for your attention, and I'm happy to answer your questions if there are some.